టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది. 2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning everyone. So in the previous classes we discussed about what is correlation, what are the types of correlation, means autocorrelation, cross correlation, etc. Now we are going to discuss about the sampling theorem. How the sampling theorem is defined. What is meant by sampling? First of all, sampling is nothing but a process of converting a continuous time signal into discrete time signal. Here the continuous time signal will flow continuously up to infinity. Okay, so it will flow continuously up to infinity. So how to convert this continuous time signal into discrete time signal? Here the in continuous time signal, let us take the sample of continuous time signal and it can be frozen for some time, so that we can divide this into equal intervals of time. That is called discrete time signal. So the process of converting the continuous time signal into discrete time signal is called sampling process. So here the continuous time signal, the sample of continuous time signal can be frozen for some time and it can be divided into equal intervals of time. That is, so discrete time signal will be formed. So like that, a continuous time signal will be converted into discrete time signal. Okay, so after sampling, the signal is defined at a discrete instance of time, and the time interval between two subsequent sampling instants is called sampling interval. What is meant by sampling interval? So here the continuous time signal will be converted into discrete time signal. So the time period between the samples and the time period between the discrete instance of time is called sampling interval. So after the sampling, the signal is defined at discrete instance of time, and the time interval between two subsequent sampling instants is called sampling interval. It is very small value. Okay, here one of the important factors is the signal sampling rate. Okay, here the important factor is signal sampling rate, which must be kept sufficiently high so that the original signal can be reconstructed from its samples. Okay, so suppose here sinusoidal signal, suppose if you take sinusoidal signal, the original signal sinusoidal signal is there, it can be converted into discrete time signal, so that it will be divided, it can be frozen for some time and it can be divided into equal intervals of time, so that discrete time signal will be formed. From that discrete time signal we can reconstruct the original signal. Okay, so that is important factor here. So here one of the important factor is the signal sampling rate must be sufficiently high. Signal sampling rate must be kept sufficiently high so that the original signal can be reconstructed from its samples. Okay, so it is represented diagrammatically like this. So see here, see here, it is x of t is the given signal. So fs sampling frequency, that is reciprocal of the time period. Okay, it will give the sampled sequence of the signals. So x of n is equal to x of nt, that is the sampled sequence. So how to get this sampled sequence? So it can be frozen for some time and it can be divided into equal intervals of time. So here if you see this diagram, so x of t is the original signal, so it can be multiplied with the delta t of t. Delta t of t is nothing but these are train of train of impulses. So these two can be multiplied so that we will get the sample sequence of the given original signal x of t, right? So x of t is the original signal which can be multiplied with the train of samples. Okay, train of samples are here like this. These are the train of samples with equal amplitude. Okay, so this is a unit amplitude, say. So this can be multiplied with the given signal so that it will give the x of nt. X of nt means the sampled sequence of x of t. So this is nothing but this diagram will explain the sampled sampling operation. This diagram will explain the sampling operation. Here, capital T is the time interval between successive samples and the sampling frequency, that is nothing but a Fs. Fs is nothing but reciprocal of the time interval, that is 1 by t h. Okay, right. So another way of representing the discrete time signal, we can represent this discrete time signal in another way also. That is excess of t. That is a discrete time signal. Excess of t is nothing but the product of the given signal x of t into the train of impulses delta t of t. Okay, let it be considered as equation number one. So that is discrete time signal xs of t is equal to the original signal x of t multiplied with delta t of t. Delta t of t is nothing but train of impulses. Okay, that was already represented in this diagram. Okay, so x of t multiplied by delta t of t, so that you will get xn of t, x of nt or xs of t, right? So that is xs of t equal to x of t into delta t of t, where delta t of t is nothing but these are train of impulses which are uh, uh, which are traveling from minus infinity to infinity. That is nt sigma, that is represented like this sigma. The n tends to minus infinity to infinity delta of t minus nt. That is equation number 2. That is the function xs of t is the product of x of t and the train of impulses, right? So it can be represented as xs of t is equal to sigma n equal to minus infinity to infinity x of nt into delta of t minus nt. Let it be considered as equation number 3. Okay, let it be considered as equation number 3. Okay, right. So now we will apply the Fourier transform for the above equation. Fourier transform for equation number 3, we will get Fourier transform of xs of t is equal to Fourier transform of sigma n is minus infinity to infinity x of nt into delta of t minus nt. Okay, or we can write this as sigma n tends to minus infinity to infinity x of nt into Fourier transform of delta of t minus nt. But we have the formula Fourier transform of delta of t minus nt, or Fourier transform of x of t is nothing but integral minus infinity to infinity x of t into e power minus j omega t dt. Like that also we can write this equation as a Fourier transform of delta of t minus nt is a delta of integral minus infinity to infinity delta of t minus nt into e power minus j omega t dt, or we can write this as the e power minus j omega nt. Why? Because delta of t minus nt is nothing but its value is 1. Okay, so integral minus infinity to infinity delta of t minus nt into e power minus j omega t dt is nothing but e power minus j omega nt, e power minus j omega nt, that is nothing but equation number 5. So we can write capital X of e power j omega is equal to Fourier transform of xs of t is equal to sigma n is minus infinity to infinity x of nt into e power minus j omega nt. Okay, e power minus j omega nt. So that is equation number 6. But we know that delta t of t is equal to sigma n is minus infinity to infinity delta of t minus nt, or we can write this as this is one relation. In earlier classes we discussed this relation, that is 1 by t into sigma m equal to minus infinity to infinity e power jm delta naught of omega naught of t. Okay, 1 by t, this can be written like this: 1 by t sigma m equal to minus infinity to infinity e power jm sigma naught of t. Let it be considered as equation number 7. Okay, where 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 omega naught is equal to 2 pi by t. So this omega naught is 2 pi by t. So xs of t is equal to x of t into this is x of t multiplied with delta t of t. So delta t of t is nothing but 1 according to equation number 7, 1 by t into sigma m equal to minus infinity infinity e power gm into delta naught of t. Or we can write this as 1 by t sigma m equal to minus infinity to infinity x of t into e power jm omega naught t. Let it be considered as equation number 8. Okay, so therefore it will become Fourier transform of xs of t is equal to 1 by t into sigma m is minus infinity to infinity Fourier transform of x of t into x of t into e power j omega jm omega naught t. Okay, that is equation number 9. So if Fourier transform of x of t is x of j omega, then Fourier transform of x of t into e power jm omega naught t is nothing but x of j into omega minus m omega naught. Okay, this is nothing but frequency shifting property. Okay, so by substituting equation number 10 in equation number 9, okay, so replace this Fourier transform of x of t into e power gm omega naught t by capital X of j omega minus m omega naught t, so that it will become Fourier transform of xs of t is equal to 1 by t into sigma m is equal to minus infinity to infinity x of j omega minus m omega naught. Let it be considered as equation number 11. Or we can write this as 1 by t into sigma m equal to minus infinity to infinity capital X of j of omega minus, here omega naught is nothing but 2 pi by t, so that 2 pi by t into m. So from this equation, this is equation number 12. From this equation we can say that the Fourier transform of the sampled signal, that is Fourier transform of xs of t, is given by an infinite sum of shifted replicas of Fourier transform of the original signal. This is the infinite sum of shifted replicas of the Fourier transform of the original signal. So Fourier transform of the sampled version of the given signal x of t, that is xs of t, is equal to 1 by t into sigma m equal to minus infinity to infinity capital X of j omega minus 2 pi by t into m. That is nothing but the infinite sum of shifted replicas of the Fourier transform of the original signal. Okay, so now consider the signal x of t is band limited to fm. Suppose it is restricted, restricted to some particular band fm. It is band limited to fm. That is nothing but it is restricted from minus fm to plus fm. It is in between minus fm to plus fm. That is the highest frequency component of x of t is fm. Then x of j omega will become 0 for mod omega is greater than omega m. Here omega equal to 2 by fm or 2 pi by t. Okay, that is equation number 13. So it is represented diagrammatically as c. This is x of j omega. It is restricted from minus omega m to plus omega m. This is frequency spectrum of continuous time signal, let us say. Okay, so coming to the diagram B, so it is excess of j omega. Excess means it is sampled version of x. Okay, it is sampled version of the above signal. Okay, right? It is like this. The sampled version of the above signal is like this. Okay, this is the frequency spectrum of x of nt with pi by t equal to omega m. Okay, next coming to the third one, that is frequency spectrum of x of nt with pi by t is greater than omega m. If pi by t is equal to omega m, then we will get the spectrum like this. If pi by t is greater than omega m, then we will get the spectrum like this. It can be expanded. Okay, so suppose in the last case we will see, if pi by t is less than omega m, it will be compressed, and there is a overlapping between these spikes. Okay, so this is the overlapping area. Okay, this is called aliasing error. This is aliasing error. So here aliasing occurs. Okay, we can prevent this aliasing error if the highest frequency component omega m or fm in the signal x of t is less than or equal to pi of t. Okay, or pi of t is greater than or equal to omega m, right? So by maintaining this condition, pi by t is greater than or equal to omega m, we can prevent this aliasing error. What is meant by aliasing error? There is a overlapping between these spikes. Okay, overlapping between the spikes. So this is the overlapping area. This is called aliasing error. How to prevent this aliasing error? By maintaining pi by t is less than or equal to omega m. Okay, pi by t is less than or equal to. Why? Because in the above two cases there is no aliasing error occurs. In the last case only this aliasing error occurs. Okay, so by maintaining pi by t is greater than or equal to omega m, we can prevent this aliasing error. So pi by t is greater than or equal to omega m. So if sampling frequency is nothing but reciprocal of the time interval, that is 1 by t, then pi into fs is greater than or equal to pi into fs is greater than or equal to omega m. Pi into fs pi by 1. Why? Because 1 by t is nothing but sampling frequency. So we can write this as pi fs is greater than or equal to omega m, or pi fs is equal to 2 pi fm. Omega m is nothing but 2 pi fm. Okay, 2 pi fm, or pi gets cancelled, so fs is greater than or equal to 2 times of fm. So sampling frequency is greater than or equal to 2 times of the frequency fm. Okay, fm, that is equation number 14. Okay, from the above discussion we can define the sampling theorem as a band limited signal, that is which is restricted between fs and fs and afs. Okay, a band limited signal x of t with a capital X of j omega is equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to 2fm. 2fm, that is sampling frequency must be at least twice the highest frequency present in the signal. Fm is nothing but the highest frequency present in the signal. So sampling theorem depends upon this condition, that is sampling frequency must be greater than or equal to double the highest frequency present in the signal. Double the highest frequency present in the signal. So finally, the sampling theorem is defined as a band limited signal x of t with with the capital X of j omega is equal to 0 for mod omega is greater than omega m. Mod omega is greater than omega m is uniquely determined from its samples, x of nt if the sampling frequency fs is greater than or equal to 2 fm. That is sampling frequency is greater than or equal to double the highest frequency present in the signal. That is nothing but the definition of the sampling theorem. Definition of the sampling theorem. They may ask this definition for 2 marks also. For 2 marks questions, define sampling theorem. Okay, then we have to write this entire definition. A band limited signal x of t with with the capital X of j omega is equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of nt if the sampling frequency, that is fs, is greater than or equal to double the highest frequency present in the signal. Okay, fs, that is fs is greater than or equal to 2 fm. Next, coming to the Nyquist rate. This is also important. What is meant by Nyquist rate? It is nothing but the minimum rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate. So the minimum rate at which a signal can be sampled. So it means that signal can be sampled in the sense it can be divided into equal intervals of the time. It means that continuous time signal can be converted into discrete time signal, and we can reconstruct the original continuous time signal from this discrete time signal. So so the signal can be sampled and still be reconstructed from its samples is called Nyquist rate. So minimum rate required, the minimum rate, okay, the minimum rate is called Nyquist rate. So it is always equal to double the highest frequency present in the signal, that is 2fm, where fm is the maximum frequency component present in the signal. Okay, suppose a signal samples at is greater than the Nyquist rate, which is said to be oversampled. Okay, suppose it is less than the Nyquist rate. Nyquist rate is 2fm. So if it is less than 2fm, then it is called undersampling. So here two conditions are there. If the signal samples are greater than the Nyquist rate, signal samples are greater than 2fm, then we can say that it is oversampling. If it is less than the Nyquist rate, we can call this as undersampling. Okay, next coming to the anti-aliasing filter. Aliasing filter and anti-aliasing filter. Aliasing already we discussed. Aliasing means there is a overlapping of this spectrum, overlapping of the spikes in the frequency spectrum. Okay, how to avoid this aliasing condition? Pi by t is greater than or equal to omega m. Pi by t is greater than or equal to omega m. Then aliasing error can be prevent. We can prevent the aliasing error. So coming to the anti-aliasing filter, okay, filter that is used to reject high frequency signals before it is sampled to reduce the aliasing is called an anti-aliasing filter. Okay, before the sampling. Okay, so a filter, it is nothing but a filter which is used to reject the high frequency signals, which is used to reject the high frequency signals before it is sampled to reduce the aliasing error is called anti-aliasing filter, which is shown like this. So this is anti-aliasing filter, right? It will take the input signal x of t. So here before the sampling only we are applying this anti-aliasing filter to reduce the aliasing error. Okay, so that we will get anti-aliasing anti-aliasing filter prior to the sampler. Okay, we can get x of n like this. Okay, next coming to the signal reconstruction. Here in the before session, what we have discussed is the signal can be converted into continuous signal can be converted into uh, discrete time signal. Discrete time signal means how to get discrete time signal. So here the continuous time signal x of t can be multiplied with the train of samples delta t of t, so that we will get the discrete time signal. So from that discrete time signal, we can get the original signal. Okay, discrete time signal, we can get the original signal. Okay, right. As we already discussed earlier, that the band limited signal x of t can be reconstructed from its samples. Band limited signal x of t can be reconstructed from its samples if the sampling rate is above the Nyquist rate. If the sampling rate is above the Nyquist rate. What is meant by Nyquist rate? Uh, it is the minimum rate at which the signal can be sampled and it can be reconstructed. Okay, it can be reconstructed from its sampled signal. Okay, that is called the Nyquist rate. So that was discussed earlier. Okay, right. So let the sample signal excess of t was a sampling with sampling period t seconds is excess of, let us take the sample signal excess of t as mathematically represented as sigma n equal to minus infinity to infinity x of nt into delta of t minus nt. That is equation number 1. Now we'll take the Fourier transform of excess of t, which was already derived in our earlier session as this one, as this equation number 12. So okay, so equation number 12, that is x of e power j omega is equal to 1 by t into sigma m is minus infinity to infinity capital X of j of omega minus 2 pi m by t, right? That is equation number 2. So the frequency spectrum x of e of j omega consists of an infinite sum of shifted replicas of the frequency spectrum of the original signal. This was already discussed in equation number 14. To get the original spectrum, the signal excess of t is to be passed through a reconstruction filter. What is meant by reconstruction filter? It is nothing but a low pass filter. What is meant by low pass filter? Low pass filter is nothing but it can allow the lower frequency components through it. Okay, so it is a filter which allows the lower frequency components, right? So that is a reconstructed filter with an impulse response h of t. Okay, how to get the original signal from the sampled signal? So the signal can be passed through a reconstruction filter. The signal can be passed through a reconstruction filter with an infinite response, with an impulse response h of t. What is meant by reconstructed filter? Reconstruction filter. Reconstruction filter is nothing but a low pass filter. What is meant by low pass filter? It which allows only lower frequency components, right? So simply it can be represented like this. So here excess of t is a sampled version of the signal which can be passed through a reconstruction filter with impulse uh, impulse function h of t. So that original signal x of t can be obtained. Okay, the original signal can be obtained by convolving the sample signal xs of t and the impulse response h of t of the filter. That is, by taking the convolution of xs of t and h of t, we will get x of t. So x of t is equal to xs of t convolved with h of t. So xs of t is nothing but sigma n is minus infinity to infinity x of nt into delta of t minus nt. The whole thing can be converted with the h of t. Okay, so it can be represented. So convolution formula is integral minus infinity to infinity sigma n is minus infinity to infinity x of nt into delta of t minus nt into h of t minus tau d tau. Okay, delta of tau minus nt is equal to 1 for tau is equal to nt. Otherwise, it is 0 for tau is not equal to nt. So, x of t becomes a sigma n is minus infinity to infinity x of nt into integral minus infinity to infinity delta of tau minus nt into h of t minus tau d tau. Okay, so therefore x of t equal to sigma n is minus infinity to infinity x of nt into h of t minus n tau h of t minus n tau. That is equation number 3. Okay, so the frequency response of the low pass filter can be expressed as h of j omega. H of j omega is equal to capital T for mod omega is less than or equal to omega s by 2. Omega s is nothing but sampling frequency. Okay, half of the sampling frequency, or it is equal to 0 for mod omega is greater than omega s by 2. Okay, it is less than or equal to omega s by 2. It is a t with from here it is 0 up to here it is 0. So that is h of j omega, which is nothing but the frequency response of the low pass filter. Low pass filter is nothing but reconstruction filter. Okay, so the impulse response of the low pass filter is h of t, right? So h of t is equal to 1 by 2 pi into integral minus tau s by minus omega s by 2 to omega s by 2 into h of j omega into e power j omega t d omega. Or we can write this as t by 2 pi into integral omega minus omega s by 2 to the omega s by 2 into e power j omega t d. Why? Because h of j omega value is t, capital T, during this interval. That's why we can replace h of j omega by t. So t is constant. That's why we can extract it outside. Okay, t by 2 pi into e power integral e power j omega t d omega, or we can write this as t by t by pi t into sine omega s t by 2. Okay, so it will become t by pi t into sine pi t by t, or it is t by pi into sine pi t by t by t. Okay, pi t by t by t. Okay, so this is equation number 5. Then we can write h of t minus nt as t by pi into sine pi by t into t minus nt by t minus nt. That is equation number 6. So substituting equation number 6 in equation number 3. What is equation number 3? This is x of t equals sigma n is minus infinity infinity x of nt into h of t minus tau. So we can write x of t as sigma n equal to minus infinity infinity x of nt into sinc pi by t. This is called sinc function. Okay, sinc pi by t into t minus nt. That is equation number 7. So here sinc function spreads over entire time axis. To reconstruct the signal at a time t equal to t naught, we must know all the sample values including those for nt greater than t naught. So it represents a non-causal system. Hence, this type of reconstruction is not suitable for real-time applications. For real-time applications, this type of reconstruction is not suitable. Therefore, we need a different approach to convert digital signal to analog signal or discrete signal into analog signal. So this type of output will not suitable for real-time applications. For real-time application, we'll go for the another approach, that is here digital to analog converter produces an output voltage that is proportional to the value of the binary word. Okay, here we are using the digital to analog conversion. Digital to analog conversion. So here DAC. So DAC is the digital to analog converter. Here sample version x of sample version of x of t, that is x of n, is given here. After digital to analog converter, an interpolator is introduced, that is which converts the output samples of DAC, digital to analog converter, into an analog signal. Okay, here we will get analog signal xa of t. So this analog signal can be passed through a low pass smoothing filter. Okay, analog signal can be passed through a low pass smoothing filter, so that we will get the pure analog signal as the output by introducing the interpolator, which will convert the DAC output signal into analog analog signal. Okay, analog signal. Output samples of DS into analog signal, which can be smoothened by using low pass smoothing filter, so that we will get pure analog signal, that is X of t. Okay, this is here. This is for real time applications only. Otherwise, the earlier one is enough. Equation up to equation number 7, which is enough. For real time applications only, we are introducing DAC, digital to analog conversion, and interpolator. Okay, right. Next, coming to the zero order hold. Okay, next, transfer function of zero order hold. What is meant by zero order hold? Okay, zero order hold. So one of the most widely used interpolator, this is one of the interpolator zero order hold. In this technique, a given sample is hold for an interval until the next sample is received. Okay, so given sample is hold for an interval until the next sample is received. After getting the next sample only, it can be released. Up to that, it will be hold. So it will be hold. So the given sample is hold for an interval until the next sample is received. Okay, next sample is received. So mathematically, it is represented as xa of t cap is equal to xn for nt is less than or equal to n is less than or equal to n plus 1 into t until the next sample is received. It can be hold until the next sample is received, where n is 0, 1 to up to n. That is equation number 8. In particular, xa of t cap is equal to x of 0 for here n is 0. So here n 0 into t, that is 0. Here n is 0 plus 1, that is 1. So it is in between 0 and t. If n is t, then it is t is less than or equal to uh, uh, 1 plus 1. here n is 1, here 1 into t. If it is 2, then 2t is less than or equal to t is less than or equal to 2 plus 1, that is 3t, like this. Okay, so zero order hold here, zero order hold is uh, it holds the it holds it holds the sample for an interval until the next sample is received. The given sample is hold for an interval until the next sample is received. So this is x of n t, say. So zero order hold is this one. So here the output will be like this. The impulse response of a zero order hold is given by h of t equal to 1 for 0 is less than or equal to t is less than or equal to t. Otherwise it is 0. This is equation number 10. Okay. So it is nothing but it holds the sample until the next sample is received. Okay, the given sample is hold for an interval until the next sample is received. So zero order hold is one of the interpolator technique. Okay, next coming to the transfer function of the zero order hold. Transfer function of the zero order hold. Okay, transfer function of the zero order hold. So the output of zero order hold is expressed in terms of h of t. So h of t is the output of zero order hold. So the output of zero order hold is expressed as h of t. That is the output xa of t cap is the convolution of x of n t and h of t. X of n t and h of t. So xa of t is equal to, convolution can be represented as equation number 11 as sigma n equal to minus infinity to infinity x of nt into h of t minus nt. H of t is equation number 10. H of t in equation number 10 can be expressed as h of t equal to u of t minus u of t minus nt. That is equation number 12. So in general, h of t minus nt is nothing but u of t minus nt. So replace t by t minus nt in the above expression. Okay, I'm substituting equation number 13 in equation number 11 so that it will we will obtain xa of t is equal to xa of t cap is equal to equation number 11 sigma n equal to minus infinity infinity x of nt into h of t minus nt is replaced by equation number 13. Okay, so taking Laplace transform on both sides, we get Laplace transform of x of t cap is equal to sigma n equal to minus infinity infinity x of nt into Laplace transform of this entire function. So finally we will get sigma n equal to minus infinity infinity x of nt into, so Laplace transform of u of minus sn u of t minus nt as e power minus snt by s minus e power minus s into n plus 1 into t by s. So already Laplace transform we have to study in the next unit. So up to here it is enough, I think. Okay, in the next chapter, we will know about the Laplace transforms and jet transforms. So by simply substituting and applying the Laplace transforms here, we will get the transfer function of the zero order hold, that is xa of s by x of s cap or x of s star is equal to 1 minus e power minus st by s. So we can say that the output of zero order hold consists of higher order harmonics. So to remove this higher order harmonics of the output of zero order hold, which is applied to a low pass filter. So to remove this higher order harmonics, we have to apply this transfer function to a low pass filter as shown in figure 1. So figure 1 is this one. Okay, zero order hold. Okay, so this is the figure 1. Okay, this is the figure 1. So this can be applied to a low pass filter. Okay, this filter is often called a smoothing filter because it tends to smooth the corners on the step approximations. So it can be smoothen the corners on the step across approximation. That's why it is called a low pass smoothing filter. Low pass smoothing filter, right? So this is the transfer function of the zero order hold. That is one of the interpolator technique. So next we will see a problem. This is the last problem in this unit. That is, see, find the convolution of two finite uh, two finite sequences given below, and also verify the result by using using the this is a treasurer method. This is called treasurer method. Okay, treasurer method. Find the convolution of two finite sequences. So here these are the two finite sequences given, and we have to verify the result by using treasurer method. Treasurer method. So here x of n is given as 2 for 0 is less than or equal to n is less than or equal to less than 3, or which is 0 otherwise, and y of n is given as 1 2 is a set of some values 1 2 3 2 1, and some arrow mark is given at the place of 3. Okay, so that we can write from this expression, we can write the x of n function as x of x of n equal to 2 for 0 is less than or equal to n is less than 3. Okay, suppose if you write otherwise it is 0. If we write 0 at here, if it is 0, x of 0, here x of 0 equal to 2. Okay, from 0 to 3, from the values of 0 to 3, its value is 2 only. Okay, and otherwise it is 0. It means that minus 1. If it is minus 1, x of minus 1 is 0. Okay, it is not equal to 3, it is less than 3. So below 3 up to 2. So up to 2 its value is 2 only, and below 0 its value is 0. So x of minus, from this mathematical expression we can write the values of this x of n function as x of minus 1 is equal to 0, x of 0 equal to 2, x of 1 equal to 2, and x of 2 equal to 2. So from this we can write x of n as 2 2 2. So this 2 is x of 0, this 2 is x of 1, this 2 is x of 2, right? So x of 0 is 2. So that's why we'll put an arrow at here. It means that x of 0 value is 2 at this arrow means this is x of 0 value. If you put arrow at here means this is y of 0 value, y of 1 value is 2, y of 2 value is 1, y of minus 1 value is 2, y of minus 2 value is 1. So here we write the values of this y of 0, y of minus 1, y of minus 2, y of 1, and y of 2 like this. Okay. So by replacing the independent variables n by a dummy variable k. So this in this above values n can be replaced by k in x of n and y of n, so that x of k is equal to 2 to 2. Arrow will be arrow, we will put arrow at here. That is nothing but x of 0 is 2, x of 1 is 2, x of 2 is 2. Similarly, y of k equal 1 2 3 2 1, y of 0 is 3 3, y of 0 y of 1 is 2, y of 2 is 1, y of minus 1 is 2, and y of minus 2 is 1. Now, h of n is nothing but x of n convolved with y of n, right? H of n is nothing but x of n convolved with y of n. So, what is the convolution formula? Sigma k equal to minus infinity into x of k into y of n minus k. Okay, so it is equal sigma x of k. Here it is varying from 0 to 2, right? 0 to 2, right? So sigma k equal to 0 to 2 x of k into y of n minus k. That is equation number 1, right? So now we'll expand this equation number 1. We get how to expand this equation number 1. Here it is varying from 0 to 2. So substitute 0 first, then 1, then 2. So if you substitute 0 at here, so this will become x of 0 into y of n minus 0. That is x of 0 into y of n, plus if it is 1, x of k into y of n minus 1, x of 1 into y of n minus 1, plus x of 2 into y of n minus 2, right? So left hand of h of n is equal to left hand of x of n plus left hand of y of n. Okay, left hand of x of n. What is left hand of x of n? What is left hand of x of n? So this is x of n. arrow market here. Left hand of x of n is 0. There is no left hand. Okay. Then what is the left hand of y of n? Left hand of y of n, in the negative side we have two values. Okay. Left hand of y of n is minus 2. Okay. 1 1 2 minus 2, so it will become minus 2. Okay, so right hand of h of n. Next, similarly, right hand of h of n, as right hand of h of n is equal to right hand of x of n plus right hand of y of n. So what is right hand of x of n? We, after this arrow we have two values, that's why it is 2. After this arrow we have two values, it is also 2. These two are in positive side only, that's why we'll get positive values. Here in the above case, here left hand of y of n is negative values, that is we'll put minus 2 here. In the same manner we'll put plus 2 and plus 2 here. 2 plus 2 equal to 4. Okay, is it clear? Right. Then that is h of n got to be computed from minus 2 to 4 only for n equal to minus 2. So here h of n, left hand of h of n, right hand of y of n is 4. So it is computed from minus 2 to 4, minus 2 to 4 for n equal to minus 2. Suppose for n equal to minus 2, h of minus 2 becomes h of minus 2 equal to h of minus 2 equal to, for n equal to minus 2, h of minus 2 becomes x of 0 into y of minus 2 plus x of 1 into y of minus 3 plus x of 2 into y of minus 4. So x of 0 value is, what is x of 0 value? X of 0 value is 2, x of 0 value is 2, x of 1 is 2, x of 3 is 2. Like that, we'll substitute those values. X of 0 is 2, y of minus 2 is y of minus 2 value is 1. Okay, so 1. Like that, we'll substitute those values, we'll get h of minus 2 will become 2, right? H of minus 2 will become 2. Similarly, h of minus 1 will become 6. H of 0, h of 1, h of 2, h of 3, h of 4. Like this, we'll get the sequence of h of n as 2, 6, 12, 14, 12, 6, 2. So h of 0 is 12, we'll put arrow at here. So this is h of 0 value, this is h of minus 1 value, h of minus 2 value, h of 1 value, h of 2 value, h of 3 value, h of 4 value. Like this, this is nothing but the treasurer method. Okay, this is nothing but the convolution of two finite sequences. Okay, this is the convolution of two finite sequences. This is about the convolution problem, and above one is a sampling theorem and reconstruction of the signal. In this I will conclude the today's session. In the next class we'll discuss about the next unit. Okay, right. Thank you. Thank you.